In this experiment, students would investigate the changes in mechanical and volumetric efficiencies of a reciprocating compressor under different compressor load and pressure ratio of compression, compare the Carnot refrigeration cycle with a practical refrigeration cycle, and find the index of polytropic compression. Carnot refrigeration cycle is a reverse heat engine cycle. Due to the mechanical work input to the cycle, heat is absorbed at a low temperature source and rejected to a high temperature sink. As every process in a Carnot refrigeration cycle is reversible, it is the most efficient refrigeration cycle. Heat Q1 is extracted at the constant temperature T1 per kg of working substance, an isothermal process 4:1 as shown in the diagram. The heat Q2 is rejected at constant temperature T2 per kg of working substance, an isothermal process, that is constant temperature. The refrigeration cycle is completed by an isentropic, that is constant entropy, compression 1:2 and an isentropic expansion process 3:4. However, the practical cycle is different from the ideal one. The compressor characteristics are the main influence affecting the cycle. In addition, the pressure losses in all connecting tubing increase the power requirement for the cycle, and also the heat transfer between the various components make the cycle deviate from the theoretical cycle. The coefficient of performance of a refrigerator COP is the ratio of refrigeration effect to the work input of the cycle. The result is compressor suction refrigerant temperature over the increased refrigerant temperature at compressor delivery. This PV diagram is an idealized cycle of the reciprocating refrigerant compressor. When the delivery stroke BC is completed, the clearance volume VC is full of gas at pressure P2 and temperature T2. As the piston proceeds on the next induction stroke, the air expands behind it, until the pressure P1 is reached. Ideally, as soon as the pressure reaches P1, the induction of fresh gas will begin and continue to the end of this stroke at A. The gas is then compressed according to the law, PV power N equal constant, and delivery begins at B as controlled by the valves. The effect of clearance is to reduce the induced volume at P1 and T1 from Vs to Va minus Vd. The masses of gas at the four principal points are such that Ma equals Mb, and Mc equals Md. The mass delivered per unit time is given by Mb minus Mc, which is equal to that induced, given by Ma minus Md. The properties of the working fluid change in processes 1:2 and 2:1 like this. Since the net work done by the piston on the refrigerant vapor in each cycle is, integrate PdV, the net compressor work can be found by measuring the area enclosed by the actual PV diagram. This PV diagram can be produced by an indicator fitted to the cylinder of the compressor. The net work done so evaluated is called the indicated work. In addition to the indicated work has to be input to the compressor for overcoming friction in the compressor, that is the shaft work, which is the sum of the indicated work and the friction work. The mechanical efficiency of the compressor is defined as the indicated power over shaft power. If both the compression and expansion processes are assumed polytropic, knowing the properties and state of refrigerant at A and B allows the polytropic index, N, to be evaluated. The equipment to be used for carrying out this experiment is the refrigeration laboratory unit manufactured by P.A. Hilton. It consists of a twin-cylinder compressor driven by an AC motor through belt and pulleys, a water-cooled refrigerant condenser, a thermostatic expansion valve and evaporator. Input heat load to the evaporator is generated artificially by electric heating elements at the evaporator, under the control of a variable transformer. The refrigeration unit is equipped with the necessary instruments and devices for measuring flow rate, pressure, and temperature of refrigerant and cooling water at various locations, and a dynamometer for measurement of motor torque output, and a built-in tachometer to measure rotational speed of the compressor. The motion of cylinder compressor is powered by an AC motor through belt and pulleys. The refrigerant would be compressed and pushed to the condenser. When the refrigerant flows through the condenser, some of the heat energy would be absorbed and carried away by the cooling water. Then the refrigerant passes through the expansion valve, its pressure would be lowered. At this moment, the temperature of refrigerant is very low. An electrical heat load is equipped at the evaporator. Students can adjust the loading along the experiment. So, at this stage, refrigerant with low heat energy would absorb and carry away the heat energy generated from the heat load. Then the refrigerant is transferred back to the compressor. This is the refrigeration cycle in this equipment. In Stage 1, students should familiarize with the setup of the equipment first. Before switching on the power, please ensure that the cooling water supply for the condenser is turned on and maintained at the maximum flow rate. Also, please check if the electricity is properly connected. Adjust the flow rate of cooling water through the condenser at about 40 grams per second. Set the evaporator heat input control to the minimum position by turning the control knob fully anticlockwise. Now, switch on the unit, and let the unit run for 4 to 5 minutes to allow it to achieve steady operation. Increase the heat load to the evaporator in steps of about 200 watt, and adjust flow rate of cooling water, such that the compressor discharge pressure is maintained within the range of 1100 kN per square meter. Remember, allow the unit to achieve steady operation after each step of load increment before taking your readings. To read the gauge pressure, the unit is in kN per square meter. As shown in this photo, the gauge reading is 1000 kN per square meter, which equals to 10 bar. The absolute pressure is the sum of gauge pressure and atmospheric pressure. So, see the example. Shaft power output of the motor is to be measured by using the spring balance, which gives reading of the free acting at the arm for balancing the torque developed. To obtain the reading, move the upper end of the spring balance until the spring balance reading. Rotational speed of the compressor shall be measured for each test run by reading the built-in tachometer. The mass flow rate of refrigerant is measured by the R134A flow meter, and the value of specific volume is read from the pH diagram. We assume there is no pressure loss in the system. The suction pressure P1 is equal to evaporator pressure, and the discharge pressure P2 is equal to condenser pressure. The temperature values of refrigerant in different refrigeration process can be read in the screen, from channel 1 to 4. As mentioned, repeat the procedures with increasing heat load to the evaporator in steps of 200 watt, until the load reaching 1000 watt. And remember to allow the unit to achieve steady operation after each step of load increment before taking your readings. After the test, turn the evaporator heat input to 0, and after 1 minute, switch off the electricity supply, and then turn off the cooling water. Remember to record the data in table along the experiment. Then draw the refrigeration cycles on pH diagram, and you could obtain values of specific volume on the diagram. First, draw the pressure lines. Pay attention to the unit of pressure used on the diagram. Point the compressor suction temperature of refrigerant T1 on the right-hand side of evaporation pressure line. Then point the compressor delivery temperature T2 on the right-hand side of condenser pressure line. Line up 2 points, and you get the compression line. Point the expansion valve inlet temperature of refrigerant T3 on the left-hand side of condenser pressure line. Draw a straight line vertical down to the evaporation pressure line. You get the line of expansion. Now, the refrigeration cycle is drew. Draw the cycles of other sets of data on the same diagram like this. You could compare the changes. Look at the top corner on the right-hand side of the pH diagram. You would find the curves of refrigerant density, which are highlighted as blue dotted curves here. The value of specific volume of refrigerant can be obtained by simply 1 over density. So, in the calculations, we need the value of specific volume of refrigerant at intake condition. First, point at the compressor suction, which is the point of T1. Follow the dotted curve to the right, you can get the value of density. Then specific volume can be obtained by using 1 over density. When we get the value of specific volume of refrigerant at intake condition V1, the refrigerant volume intake rate can be calculated. The total swept volume of compressor Vs equals double of the swept volume of cylinder, as our compressor is a twin-cylinder design. Afterwards, you can get the clearance volume Vc. Calculating the mechanical efficiency, it is the value of indicated power over that of the shaft power. And we can get the result by means of inputting the value of spring tension. Volumetric efficiency, it involves the parameters of refrigerant mass flow rate, specific volume of refrigerant at intake condition, compressor total swept volume and compressor rotational speed. In the calculation, pay attention to the unit of the parameters. Finally, to calculate the index of polytropic compression and expansion, we can make use of the equation of actual volumetric efficiency. We can get the result of N by the log method. Students can take this as example and carry on for other sets of data. In the logbook report, please complete the refrigeration cycles and calculations, plot the relationship between efficiencies and compressor load, and compression pressure ratio. Then try to do the supplementary. Enjoy the experiment. Thank you.